Mars has long been the symbol of humanity's future in space. It is dry, familiar, and always within the imagination of the next great mission. But far beyond Mars, hidden beneath a thick golden haze, Titan may offer something even more valuable, a world with lakes, rivers, weather, complex organic chemistry, and secrets that could reshape how science understands life's building blocks in the cosmos. If this journey into Titan's mystery sounds fascinating, please like the video, subscribe to the channel, and settle in for a deeper look at why Titan might one day matter even more than Mars. Far from the inner planets, Saturn moves in a wide path around the Sun, carrying rings and many moons through a region where sunlight is weak and cold is persistent. The planet's orbit lies at roughly 9.5 astronomical units from the Sun on average, so the energy arriving from the Sun is only a small fraction of what reaches Earth. In this distance, warming and cooling proceed slowly. The outer solar system is not empty, yet compared with the inner region it is thinly supplied with dust and gas. Small grains drift between orbits, shaped by gravity and by the gentle outward pressure of sunlight, while Saturn's own gravity dominates the local space, gathering some material into rings and clearing other paths. Saturn's year is long. It takes about 29.5 Earth years to complete one orbit. This length matters because seasons in a planetary system depend on time as well as on geometry. Saturn's axis is tilted by a little more than 26 degrees relative to its orbital plane, which gives the planet and its moons seasons that shift as Saturn moves around the Sun. Each season lasts for more than 7 Earth years. In such conditions, changes linked to sunlight can build gradually, with long intervals of increasing light and long intervals of fading light. When sunlight is scarce, the contrast between sunlit and shadowed regions becomes sharp, and the placement of shadows can matter for temperatures over long spans. The environment around Saturn is also shaped by magnetism. Saturn has a strong magnetic field that forms a magnetosphere, a region where charged particles are guided by magnetic forces. The magnetosphere contains plasma, which is gas with many particles carrying electric charge. Some of this plasma comes from the solar wind, a stream of charged particles flowing outward from the Sun. Some comes from within the Saturn system, supplied by the rings and by moons that release atoms and molecules into space. The magnetosphere changes with time. When the solar wind pressure rises, the outer boundary can be pushed inward. When it falls, that boundary can expand outward. These shifts change where energetic particles travel and where they can reach. Radiation in the Saturn system comes from several sources. Sunlight provides ultraviolet light that can break apart molecules in thin gases. Energetic particles trapped within the magnetosphere can strike surfaces and atmospheres, changing chemistry and altering materials over time. There's also cosmic radiation arriving from outside the solar system, made of very high energy particles that can penetrate deeply into matter. At Saturn's distance, the lower intensity of sunlight reduces heating, yet ultraviolet light still arrives, and magnetospheric particles provide an added energy source. The balance between these inputs differs from that nearer the Sun, and it becomes one of the defining conditions for any moon with a substantial atmosphere. Saturn's rings add structure to the surrounding space. They spread outward in a flat plane close to Saturn's equator. Most of the ring material is water ice, broken into countless pieces ranging from tiny grains to blocks many meters across. The rings are not a solid sheet. They're a swarm of particles, each following its own orbit while colliding and exchanging energy. In some places, gravity from nearby moons creates gaps, waves, and sharply defined edges. The rings reflect sunlight strongly, so they can be bright against the dark sky. And they cast wide shadows that shift with the seasons. Beyond the rings, Saturn's moons occupy many different orbits. Some are small and irregular, likely objects captured long ago, moving on tilted or elongated paths. Others are large and nearly spherical, shaped by their own gravity. The moons interact through gravity, and repeated tugs can keep some orbits slightly stretched. This matters because a stretched orbit produces changing tides, the varying pull of gravity during a circuit, which can flex a moon and generate internal heat. Even far from the sun, this kind of heating can be significant for some bodies, showing that local energy sources can rival sunlight in shaping a world. Within this broader setting, Titan travels around Saturn as one of the largest moons in the solar system. Its orbit lies well beyond the main rings, at a distance of more than 1 million kilometers from Saturn's center. At that range, Titan spends much of its time inside Saturn's magnetosphere, though the moon can also pass through regions influenced more directly by the solar wind when the magnetosphere is compressed. This shifting passage affects the charged particle environment around Titan and contributes energy to its upper air. Titan's orbit is close to circular, and it completes one circuit around Saturn in a little less than 16 Earth days. This motion establishes a repeating rhythm of illumination and particle exposure that is set by the geometry of Saturn, the Sun, and the moving boundary of the magnetosphere. This Sun remains the primary source of light for Titan, yet at Saturn's distance the solar input sets a cold baseline. In the outer Saturn system, temperatures are far below freezing on Earth. Water ice is rigid like rock under these conditions, and many substances that are gases in warmer places become liquids or solids. Methane and ethane can condense. Nitrogen can approach a liquid state in the coldest situations, and the mechanical behavior of common materials shifts. Chemical reactions continue, but their rates and pathways are influenced by low temperatures and by the availability of energy from ultraviolet light and energetic particles. This outer setting also constrains exploration. Travel times from Earth are long, often measured in many years. Spacecraft must operate where sunlight is weak, so electrical power often relies on sources other than solar panels, and systems must withstand deep cold. Communication distances are vast, so signals take a long time to cross space, and data rates are limited. These constraints shape what can be observed and how long a mission can endure. Even with these limits, the Saturn system provides a coherent natural laboratory. It gathers varied environments into one gravitational family, and it sets the stage for Titan by supplying the cold, the seasonal rhythm, and the streams of charged particles that act on its outermost air. Against the dark background of the outer Saturn system, Titan appears first as a muted disk rather than as a sharply defined moon. From a distance, it does not present the bright, hard surface seen on many icy bodies. Its outline is softened by a surrounding shell of atmosphere, and its visible colors are subdued by suspended particles that scatter and absorb light. This makes Titan distinct even before details can be measured. Among Saturn's many moons, it stands apart not only because of its size, but because it is wrapped in air dense enough to hide the ground beneath. The first view from afar is therefore not a view of terrain, it is a view of a world enclosed. Titan is the largest moon of Saturn, and the second largest moon in the solar system after Jupiter's Ganymede. Its diameter is about 5,150 kilometers, which makes it larger than the planet Mercury in total size, though much less massive. Size alone does not explain its importance. Yet size determines gravity, and gravity determines whether a body can hold on to gases over immense spans of time. Titan's surface gravity is only a little more than 1/7 of Earth's, but its low temperatures help it retain a substantial atmosphere. Molecules move more slowly in cold conditions, so fewer can escape into space. This simple balance between gravity and temperature is one of the first reasons Titan looks unlike most moons. Seen from far away, Titan reflects sunlight in a way that reveals the dominance of its atmosphere. The visible disk has a soft orange cast. This colour does not come from exposed rocks or from a sea reflecting the sky. It comes mainly from a high haze made of tiny particles formed by chemical reactions in the upper atmosphere. Sunlight enters, interacts with gases and aerosols, and emerges altered. Shorter wavelengths are scattered and absorbed differently from longer wavelengths, producing a muted amber tone. In ordinary visible light, the surface remains hidden. The eye meets atmosphere first, and then more atmosphere behind it. Because Titan is enclosed by this haze, early telescopic observations from Earth could measure only broad properties. Astronomers could determine its orbit, estimate its size from geometry and brightness, and note that it behaved differently from a bare icy moon. The stronger proof of a dense atmosphere came gradually through spectroscopy, the study of how matter absorbs and emits light at specific wavelengths. Spectroscopy allows gases to be identified by their patterns. In Titan's case, observations revealed methane early on, and later work established nitrogen as the main atmospheric component. Even so, the distant view remained limited for a long time. The haze concealed direct information about the surface and forced observation to rely on wavelengths of light that can penetrate better than visible light can. The outer appearance of Titan also changes with geometry. As the angle between the Sun, Titan, and the observer shifts, different scattering effects become visible. At some angles, the atmosphere produces a bright edge where sunlight passes through long paths in the haze. At other angles, the disk appears flatter and less contrasted. These variations are valuable because they reveal how particles are distributed in height and size. A world without much atmosphere would simply brighten or dim as an illuminated sphere. Titan does more than that. It glows around the edges, softens its own boundary, and stores information in the changing path of light through its air. The first spacecraft views confirmed and deepened this impression. Flybys by Pioneer and Voyager provided measurements of Titan's diameter, temperature, and atmospheric character. But they still did not reveal the ground clearly. The haze remained a veil. This fact was scientifically important in itself. It meant that Titan was not merely a moon with a trace atmosphere. It was a planetary body with a fully developed gaseous envelope, one capable of blocking direct optical access to the surface. Later, the Cassini mission and the Huygens probe transformed understanding by using instruments sensitive to infrared wavelengths, radar, and in situ measurements. Yet even before the details of lakes, dunes, and channels became known, Titan's distant face had already identified it as an unusual place in the solar system. From afar, brightness measurements also reveal that Titan is not uniformly reflective. The atmosphere scatters light strongly. But different layers and regions contribute differently depending on wavelength and season. Seasonal changes alter the distribution of haze and clouds, and these changes slightly modify the Moon's appearance over years. Since Saturn takes nearly 30 Earth years to orbit the Sun, Titan's seasons are long. The distant observer therefore sees not a static sphere but a slowly changing one. This slow rhythm is one of Titan's defining visible traits. It is not dramatic on human timescales, yet it is measurable and orderly. There's also an important contrast between Titan and Mars embedded in this first view. Mars, from afar, usually presents a surface world. Dust storms may blur it, polar caps may grow and retreat, and thin clouds may pass overhead. But the ground remains the dominant visible feature. Titan presents the opposite balance. Its atmosphere dominates the visual identity, and the surface is withheld. This difference shapes scientific priorities. A world whose visible character is atmospheric invites questions about chemistry, circulation, and climate before geology can even be seen. The very difficulty of seeing the ground makes the atmosphere central to understanding the Moon as a whole. The distant appearance of Titan also carries clues about energy. A thick haze changes how sunlight is absorbed and where warming occurs. Instead of a simple case where light reaches the ground and heat returns upward, Titan redistributes incoming energy through atmospheric particles and gases. Some wavelengths are blocked high above the surface. Some infrared radiation is trapped more effectively than it would be in clear air. These processes affect temperature structure, cloud formation, and the stability of surface liquids. Even without a close view, the remote disk implies a complex climate system. The outward look of Titan is therefore not decorative. It is diagnostic. In the end, the first view of Titan is the view of a moon that behaves like a small planet. It has enough size to retain a massive atmosphere, enough distance from the sun to remain deeply cold, and enough chemical activity aloft to create a global haze. Its outward form is not shaped by exposed stone or bare ice, but by air, suspended particles, and slow seasonal change. Before any descent toward the lower layers, the eye meets this broad fact: Titan is not simply an object in orbit around Saturn. It is a world whose outer identity is atmospheric, and whose hidden surface must be approached through the light that filters down from above. Above Titan's visible haze, the atmosphere becomes thin, cold, and chemically active. In this outer region, the gas is spread far apart compared with the dense air below, yet it is still substantial enough to intercept sunlight and to respond to streams of energetic particles arriving from space. The upper atmosphere begins where collisions between molecules become less frequent, and where the balance between chemistry, radiation, and escape to space becomes increasingly important. It is here that Titan first meets the external forces of the Saturn system. Sunlight, though faint at Saturn's distance, still carries enough ultraviolet energy to break chemical bonds. Charged particles from Saturn's magnetosphere and from the solar wind also enter this region and add their own effects. The result is a high atmospheric zone that is not still or passive, but continuously altered by incoming energy. The main gas in Titan's atmosphere is nitrogen. Methane is present in smaller amounts, yet it plays a central role in the upper chemistry because it is easily broken apart by ultraviolet light. When a methane molecule absorbs sufficient energy, it can split into smaller fragments. These fragments are reactive. They collide with other molecules and radicals, meaning short-lived reactive fragments with unpaired electrons, and begin chains of new reactions. Nitrogen, though more resistant than methane, also participates when enough energy is available. From these interactions, the upper atmosphere produces a wide variety of organic molecules, from simple hydrocarbons to more complex compounds that include nitrogen. In planetary science, organic here means carbon-based chemistry. It does not imply life. It simply describes the presence of carbon bonded with hydrogen, nitrogen, and other elements in molecular forms. This upper region includes the ionosphere, a part of the atmosphere where many atoms and molecules are electrically charged. Ionization happens when energy removes electrons from neutral particles. On Titan, ionization is driven by sunlight and by energetic electrons and ions from outside. The ionosphere is not a separate layer made of different gas. It is a condition of the gas at certain heights, where ionized and neutral particles coexist in significant numbers. These charged particles allow electrical and magnetic interactions that do not dominate lower down. They also open reaction pathways that lead to molecules difficult to make in denser, calmer air. Measurements from spacecraft and from radio experiments show that Titan's ionosphere is complex and variable, changing with solar illumination, local time, and the Moon's position within Saturn's magnetic environment. Temperatures in the upper atmosphere differ from those near the surface. Although Titan as a whole is very cold, the highest layers can be warmed by the absorption of radiation and by particle impacts. This does not make them warm in ordinary terms, but it changes how gases move and mix. Heating in thin air can produce expansion, altering the vertical profile of the atmosphere and affecting how quickly particles are transported upward or downward. The structure of the upper atmosphere is therefore controlled not only by composition, but by the pattern of energy deposition. In one region, ultraviolet light may dominate. In another, magnetospheric particles may contribute more strongly. These inputs are variable in time, which means the upper atmosphere is not fixed. It breathes and shifts in response to its environment. One of the key outcomes of this high-altitude chemistry is the production of heavier molecules that can no longer remain purely gaseous under Titan's conditions. As molecules combine and grow, they begin to form clusters. These clusters act as seeds for still larger particles. Over time, they become aerosols, tiny solid or liquid particles suspended in the atmosphere. The process is gradual and distributed over height, but it begins in the upper atmosphere where methane and nitrogen first absorb enough energy to react efficiently. The aerosols produced there are the ancestors of the global haze that surrounds Titan. At this stage, however, they are small and newly formed, still part of a chemical factory operating in rarefied air. The upper atmosphere also marks the region where Titan slowly loses some material to space. Escape does not mean that the atmosphere streams away rapidly. Titan has retained a dense atmosphere over long spans, which shows that loss is limited compared with the total reservoir. Even so, some atoms and molecules can reach velocities that allow them to leave, especially at great heights where gravity is weaker in effect because collisions are rare. Hydrogen, being very light, can escape more easily than nitrogen or methane fragments. Other loss processes involve interactions with plasma, which can knock particles away or help drive ions outward along electromagnetic paths. Understanding escape is important because it links present conditions to long-term history. The upper atmosphere is the gate through which Titan exchanges material with surrounding space. This region is also where observations must work hardest against distance. Instruments cannot simply photograph the chemistry directly. Instead, they detect spectra, count ions, measure mass, and track how radio signals are altered as they pass through the atmosphere. Each method adds a different piece. Spectra reveal which gases absorb or emit at certain wavelengths. Mass spectrometers identify particles by mass to charge ratio, helping distinguish molecules and ions. Radio occultation, in which a spacecraft signal passes through the atmosphere on its way to Earth, provides information about density and structure. Combined, these methods show a layered, active region in which chemistry and physics are closely linked. A notable feature of Titan's upper air is that complexity appears early. On some worlds, upper atmospheres are dominated by only a few simple species. Titan does contain major simple gases, but the chemistry quickly branches outward into an intricate network. Molecules such as ethane, acetylene, hydrogen cyanide, and many others are generated or transported there. Some descend later to lower levels, some become part of aerosol particles. This chemical richness is one reason Titan attracts so much scientific attention. It offers a natural example of carbon and nitrogen chemistry, proceeding on a planetary scale in the absence of liquid water at the surface. At these heights, Titan is still only partly itself in visible terms. The familiar orange disk is not yet formed here as a dense visual layer. Instead, the upper atmosphere is a zone of initiation. Energy enters, molecules break and reform, ions appear and vanish, and tiny particles begin to assemble. The region is open to space, yet it already carries the signatures that will shape everything below. The upper atmosphere does not reveal the surface, and it does not behave like the calm lower air. It is the exposed skin of Titan's gaseous envelope, where the outer environment first becomes chemistry, and where thin, cold gas begins the slow work of building the moon's global shroud. Below the highest chemically active air, Titan's haze becomes the defining feature of the moon's outer atmosphere. It is not a single cloud deck or a narrow band at one height. It is a broad system of suspended particles extending through much of the atmosphere, layered in ways that respond to chemistry, circulation, and season. These particles are extremely small at first, then gradually change as they move downward and interact with surrounding gases. Together they form the orange veil that hides Titan's surface in visible light and gives the moon its soft, diffuse appearance from far away. The haze is therefore not a decorative surface effect. It is a deep atmospheric structure made of matter that has been manufactured in the air itself. The starting material for the haze lies in the upper chemistry. Methane and nitrogen are altered by sunlight and energetic particles, producing a large family of organic compounds. As these compounds grow more complex, some become heavy enough to cluster into tiny solid particles. These particles are often described as aerosols, meaning fine particles suspended in gas. At Titan, they are rich in carbon and also incorporate hydrogen and nitrogen in many forms. Laboratory studies on Earth produce similar materials when methane and nitrogen are exposed to energy under Titan-like conditions. These laboratory products are often called tholins, a convenient term for a broad class of complex organic solids. On Titan itself, the exact composition is not represented by a single substance, but the term helps describe the general character of the haze particles as chemically processed organic matter. As the particles descend, they pass through regions with different temperatures, pressures, and gas mixtures. This changes their size and structure. Small particles can stick together in aggregates, meaning loose clusters built from many even smaller pieces. An aggregate does not behave exactly like a compact sphere. It scatters light differently, falls at a different rate, and presents a larger surface area to surrounding gases. These properties matter because they help determine how Titan's haze looks and how it interacts with radiation. The haze is effective at scattering and absorbing visible light, which is why the surface remains concealed to the eye. At some infrared wavelengths, however, the atmosphere becomes more transparent. Through those spectral windows, spacecraft instruments can detect hints of the ground below. The haze also influences Titan's temperature structure. When suspended particles absorb a sunlight high in the atmosphere, They warm those layers relative to what they would be in clear air. At the same time, they reduce the amount of solar energy that reaches lower levels. This creates a vertical pattern in which the atmosphere aloft can be warmed by absorbed radiation, while the surface remains very cold. The haze therefore acts as both shield and regulator. It limits direct sunlight reaching the ground. Yet it also participates in trapping outgoing infrared radiation in combination with atmospheric gases. The net effect is not a simple warming or cooling. It is a redistribution of energy across height, producing an atmosphere with a structure very different from a clear, thin sky. This optical control explains much of Titan's outward appearance. In visible light, the moon's edge is softened because light is scattered repeatedly before escaping to space. Fine particles high in the atmosphere contribute to the diffuse glow around the disk. Deeper haze adds thickness and opacity, making the moon appear as a muted sphere rather than a body with visible landforms. The orange color arises because the particles absorb and scatter wavelengths unevenly. Blues and shorter visible wavelengths are diminished more effectively, while longer wavelengths pass with different efficiency, producing the familiar amber tone. The exact shade varies with viewing geometry and with the vertical distribution of particles, but the general effect remains stable enough to define Titan in nearly every visible image. Seasonal circulation changes the haze over time. Titan's long seasons allow atmospheric motions to transport particles and gases across hemispheres over many Earth years. Observations show that detached haze layers can appear at certain heights, especially when circulation patterns shift. A detached haze layer is a region where particle density increases enough to produce a visible band separated from the main lower haze. Such layers are valuable because they reveal that Titan's atmosphere is dynamic rather than static. They indicate rising and sinking motions, changes in production rates, and the transport of aerosols over large vertical distances. These features can move or vary with season, showing how closely the haze is tied to the moon's broader climate. The haze also settles slowly toward the surface. This descent is not a rapid snowfall in the ordinary sense, but a persistent rain of organic particles over very long times. Each particle falls through dense air at a limited speed, shaped by its size, structure, and the viscosity of the gas around it. During descent, particles may collect coatings of condensed molecules, or may be altered by further chemistry. By the time they reach lower altitudes, they form part of a continual transfer of material from atmospheric chemistry to the ground. This process links the sky and the surface in a direct material way. Titan's surface is not only shaped by liquids and ice, it also receives a slow atmospheric deposit of organic solids created overhead. Another important role of the haze is in shielding the lower atmosphere from some external radiation. The upper chemistry begins with energy arriving from outside, but as particles accumulate, they absorb and scatter part of that energy before it can reach deeper levels. This reduces the direct photochemical influence of sunlight at lower altitudes and confines the most energetic reactions mainly to higher regions. The haze is therefore a mediator. It is produced by radiation, then in turn modifies how radiation continues to act on the atmosphere below. This feedback helps maintain Titan's layered character. Scientific understanding of the haze depends on combining many kinds of evidence. Imaging reveals shape and layering. Spectroscopy constrains composition and particle size through the way light is scattered and absorbed. Laboratory experiments provide analog materials that can be compared with observations. Models of atmospheric motion test whether the observed layers and seasonal changes can arise from known circulation patterns. None of these methods alone gives a complete answer. Together they show that Titan's haze is not a simple smog. It is an active, evolving atmospheric product that influences visibility, temperature, chemistry, and the delivery of organics to the surface. In this region, Titan's outer identity becomes fully established. The upper atmosphere begins the chemistry, but the haze gives that chemistry a visible body. It is the broad middle veil through which sunlight is filtered, and through which every later observation of the lower world must pass. The particles hang in layers, drift with seasonal motion, absorb and scatter light, and descend gradually toward the ground. They turn a distant moon into a muted globe and transform incoming energy into a structured climate. In the haze, Titan's atmosphere ceases to be only gas. It becomes matter in suspension, and that suspended matter shapes almost everything that can be seen from above. Below the broad haze, Titan's lower atmosphere becomes denser, calmer in appearance, and more directly tied to the conditions at the surface. The air here is still part of the same global system of nitrogen, methane, and trace compounds, yet its behavior changes because pressure rises and temperatures settle into a narrow cold range, shaped by both the weak sunlight from Saturn's distance and the insulating effect of the atmosphere above. This lower region is where gas begins to act less like a rarefied chemical medium and more like a true weather-bearing air. It is also where Titan differs most strikingly from Mars. Mars has a thin atmosphere, with a surface pressure far below that of Earth. Titan, by contrast, has an atmosphere near the ground that is denser than Earth's at sea level. The difference is fundamental. On Titan, the air is not a slight covering over the land. It is a substantial physical environment in its own right. The main gas remains nitrogen. This gives Titan a broad similarity to Earth in composition at the most general level, since Earth's atmosphere is also dominated by nitrogen. The similarity ends quickly in other respects. Titan is far colder. It contains no free oxygen as a major atmospheric gas, and methane plays an important role that has no close equivalent in Earth's present lower atmosphere. Near the surface, methane exists as a minor constituent by percentage, but it is climatically important because it can change phase under Titan's conditions. A phase change is a shift between gas, liquid, and solid. On Titan, methane can evaporate, condense, form clouds, and fall as rain. This makes it a working fluid in the lower atmosphere, even though nitrogen remains the bulk of the air. The surface pressure on Titan is about 1.5 times that of Earth at sea level. Pressure is the weight of air above a given area. Because Titan's atmosphere is deep and the Moon's gravity is modest, the lower air is dense in a way that feels unusual by inner solar system standards. This density affects how heat moves, how particles settle, how sound would travel, and how objects would move through the atmosphere. It also means that the boundary between atmosphere and surface is not harsh in the way it is on an airless moon. There's no abrupt transition from vacuum to ground. Instead, there is a continuous envelope of gas pressing gently but persistently on the landscape. Temperature near Titan's surface is close to 94 degrees Kelvin on average, which is about minus 179 degrees Celsius. At such temperatures, water ice behaves not like soft frost, but like very hard rock. Methane and ethane, however, enter a range where they can be liquid. This single fact transforms the meaning of the lower atmosphere. On Earth, the lower atmosphere exchanges water with oceans, soil, clouds, and ice. On Titan, the lower atmosphere exchanges methane with lakes, damp ground, cloud systems, and the haze-derived material that settles from above. The physical laws are the same, but the substances involved are different because the thermal environment is different. The lower atmosphere is not chemically simple. Trace gases formed higher up can descend into it, and some continue to react or condense at lower levels. Ethane, acetylene, hydrogen cyanide, and other compounds are present in small amounts, though not all remain evenly mixed near the surface. Some freeze or condense more readily than methane under Titan's temperatures. Others are present only in very low abundance yet still matter, because they reveal the long chain of atmospheric chemistry operating from the upper layers downward. The lower atmosphere is therefore a receiving zone as well as an active one. Material produced aloft enters it, mixes within it, and in some cases reaches the surface. Winds in the lower atmosphere are shaped by Titan's slow rotation, dense air, and long seasonal cycle. Near the surface, winds are often gentle, though not absent. Higher in the atmosphere, stronger winds can occur, and these can influence the transport of heat, haze, and methane-rich air masses over great distances. Titan rotates once in the same time that it orbits Saturn, a little under 16 Earth days, which means the same face always points towards Saturn. This synchronous rotation affects the Moon's day length and helps set the rhythm of heating and cooling. Even so, because sunlight is weak and the atmosphere is thick, Titan does not respond to day and night with rapid temperature swings at the surface. The lower atmosphere acts as a reservoir, damping sharp changes and favouring gradual shifts. This dense cold air also alters the mechanics of movement near the ground. A body moving through Titan's lower atmosphere encounters significant aerodynamic resistance because the air is dense, while the low gravity reduces weight. These combined conditions make flying easier in a physical sense than on worlds with thin atmospheres. Although engineering a vehicle for such cold conditions remains difficult, for natural particles, the same principles matter. Dust and organic grains settle slowly. Fine material can be kept aloft longer than might be expected under stronger gravity. The lower atmosphere therefore participates in sorting, moving, and depositing surface material over time. At the same time, the lower atmosphere shields the surface from part of the radiation environment outside. Cosmic radiation is not removed completely, and energetic influences still matter, but the dense air and overlying haze reduce the direct exposure that would occur on a world with little atmospheric protection. This is one reason Titan is often discussed as an especially interesting target for future exploration. The surface is bitterly cold and chemically alien to ordinary terrestrial conditions, yet it lies beneath a substantial atmospheric blanket rather than under near vacuum. Scientific importance does not mean ease or comfort. It means that many interacting processes can be studied together in one place. The lower atmosphere is also the zone where measurements become more direct. The Huygens probe, descending through Titan's air, recorded pressure, temperature, winds, and composition as it moved downward. These measurements confirm that the atmosphere grows steadily denser toward the surface, and that methane humidity increases in ways consistent with exchange between air and ground. Humidity here refers to the amount of methane vapor in the air relative to the amount the air can hold before condensation begins. In some regions and seasons, the lower atmosphere approaches conditions suitable for cloud formation and rainfall. This makes Titan not merely a moon with thick air, but a world where the lower atmosphere is part of an active climate cycle. In this region, Titan's atmosphere becomes fully tangible. It has weight, pressure, motion, and the capacity to carry weather. Nitrogen forms the great mass of the air. Methane gives it an active climate role, and trace organics reveal the downward reach of chemistry that begins high above. Light is dim. temperatures remain extremely low, and the surface lies under a dense, cold sky, unlike any found elsewhere in the solar system. The lower atmosphere is no longer a veil alone. It is the working medium through which Titan's climate touches the ground, and through which the Moon's broader scientific importance begins to take practical form. In Titan's lower atmosphere, methane does more than remain mixed in the air. It circulates through the environment in a repeating pattern of evaporation, condensation, cloud formation, rainfall, surface wetting, and renewed evaporation. This pattern is often called a methane cycle because it resembles, in broad physical form, the water cycle on Earth. The substances are different, the temperatures are far lower, and the timescales are shaped by Saturn's long year, yet the underlying principle remains familiar: a volatile liquid, meaning a liquid that can easily become vapor, moves between ground and sky under changing conditions of temperature, pressure, and circulation. On Titan, methane is the principal volatile at the surface and in the lower atmosphere, and this gives the Moon an active weather system rather than a static cold sky. Methane can exist on Titan as gas and liquid under surface and near-surface conditions. When liquid methane or methane mixed with other hydrocarbons is exposed to the air, some molecules escape from the liquid into the atmosphere. This is evaporation. The rate depends on temperature, wind, humidity, and the composition of the liquid itself. If the lower air is already rich in methane vapor, evaporation proceeds more slowly. If the air is drier, more methane can enter it. Once methane vapor is present in sufficient quantity, cooling or uplift can bring the air to saturation, meaning it holds as much vapor as it can under those conditions. Further cooling then causes condensation, in which methane leaves the gas phase and forms droplets or ice particles within clouds. Clouds on Titan are not constant across the globe. They appear in patterns linked to season, latitude, and atmospheric circulation. Observations from telescopes and from the Cassini mission show that clouds can form near the poles and also in lower latitude regions during certain seasonal intervals. These clouds vary in altitude and extent. Some are broad and persistent enough to indicate organized atmospheric motion. Others are more localized and temporary, suggesting shorter-lived changes in humidity and uplift. Because Titan's year is long, the migration of cloud activity from one hemisphere to the other is also slow. Seasonal sunlight gradually shifts the balance of heating, and the atmosphere responds over many Earth years. The atmosphere transports methane through large-scale circulation. Circulation means the organized movement of air over global distances, driven by unequal heating and by the rotation of the world. On Titan, the weak sunlight and dense atmosphere produce a climate that changes gently, but not weakly. Air can rise in regions where heating and humidity favor uplift, move aloft across latitudes, and sink elsewhere. During seasonal change, these patterns shift. Methane vapor is carried with the moving air, so places of cloud formation do not depend only on local evaporation. They also depend on where the atmosphere delivers moisture. This is one reason the methane weather system must be understood as a planetary process rather than a collection of isolated storms. Rainfall on Titan appears to occur in episodic events rather than in constant drizzle. The evidence comes from cloud observations, surface darkening after suspected rain, and landforms that imply repeated liquid flow over long spans. When methane condenses into sufficiently large droplets or particles, gravity causes them to fall. Titan's dense atmosphere and low gravity influence how this happens. Falling droplets move more slowly than they would in thinner air, and their shape and stability can differ from those of raindrops on Earth. Even so, the essential process remains the same. Condensed methane leaves the cloud and returns to the surface, transferring matter from sky to ground. Rain affects the surface in multiple ways. It can darken the ground temporarily by wetting it, fill shallow depressions, refresh surface liquids, and initiate runoff across slopes and plains. Runoff means liquid moving across the surface under gravity. On Titan, rainfall need not be frequent to be geologically important. A rare but intense event can carve channels, mobilize loose material, and alter the shape of drainage networks. The lower atmosphere therefore communicates directly with the surface through rainfall, making climate a driver of landscape evolution. Titan's weather is not merely atmospheric motion. It leaves marks. Methane humidity near the ground also changes with place. In some regions, especially near large surface liquid bodies, the lower air can become richer in methane through ongoing evaporation. In drier terrains, humidity may be lower. These differences matter because they control where clouds can form most easily and where liquid exchange with the surface is strongest. The polar regions, which contain Titan's largest known lakes and seas, appear to function as major reservoirs feeding atmospheric methane. Yet the cycle is not limited to the poles. Evidence for channels and rainfall effects at lower latitudes shows that methane transport reaches far beyond the standing liquids that are visible today. Ethane is also part of this weather system, though its role differs from methane's. Ethane is less volatile under Titan's conditions, meaning it evaporates less readily. It can accumulate in lakes and seas and may mix with methane there, altering the physical properties of the liquid. Nitrogen can dissolve in these hydrocarbon liquids as well. The atmosphere is therefore linked not to a single pure substance, but to a family of interacting fluids. Still, methane remains the main agent of rapid exchange between surface and sky, because it moves most readily through evaporation and condensation at Titan's surface temperatures. Seasonal forcing shapes the whole system. As Saturn proceeds around the Sun, Titan's hemispheres receive changing amounts of sunlight over spans of many Earth years. This alters circulation, cloud formation, and the likely balance between evaporation and precipitation in different latitudes. Models and observations indicate that the atmosphere can transport methane from one hemisphere toward the other as seasons evolve. Such redistribution may help explain why major surface liquid bodies are concentrated today near the poles, especially in the north, while equatorial regions show evidence of erosion and transport but are comparatively dry at present. The weather system is therefore not fixed in one arrangement, it shifts with season, storing methane in different forms and places over long intervals. There is also an unresolved aspect to Titan's methane climate. Methane in the atmosphere is broken apart by sunlight over geologic time, so without replenishment the present atmospheric supply could not last indefinitely. Observations show that methane is there now, and surface and atmospheric processes clearly recycle it over seasonal and climatic timescales. It remains uncertain how the methane inventory is maintained over much longer spans. Some combination of subsurface storage, episodic release, and long-term exchange is possible, but the exact balance is not yet fully established. This uncertainty does not weaken the reality of Titan's weather. It simply marks a deeper question about the longevity of the cycle. In Titan's methane weather system, the Moon becomes recognizably active. Liquid and vapor exchange continually under a cold nitrogen sky. Clouds gather, rainfall occurs, the ground is wetted, and methane returns again to the air. The pattern is slower than weather on Earth, and its materials are alien to ordinary terrestrial life, yet it is a true climate cycle all the same. Titan's atmosphere does not merely rest above the surface, it works upon it through methane, season after season, with enough persistence to shape the Moon's face over time. Near Titan's poles, the methane weather system comes to rest in broad, dark bodies of liquid that occupy depressions in the landscape and gather along low-lying terrain. These lakes and seas are among the most remarkable features known on any moon. They are not inferred only from theory or from subtle chemical hints. They are directly observed through radar and infrared methods that can penetrate Titan's atmospheric haze. In these observations, the liquid surfaces often appear very dark because smooth liquids reflect radar away from the instrument unless the geometry is just right, and because the cold hydrocarbons absorb and scatter light differently from surrounding solid ground. The result is a set of polar regions marked by clustered basins, winding shorelines, and extensive liquid reservoirs unlike anything known elsewhere beyond Earth. The largest concentrations lie in the North Polar region. Kraken Mare, Ligeia Mare, and Punga Mare are the principal seas, each extending across great distances and together forming a complex hydrocarbon basin system. Smaller lakes surround them in large numbers, especially in regions cut by channels and low-relief terrain. The South Polar region also contains liquid bodies, though fewer large examples are visible there at present. This asymmetry likely reflects seasonal and climatic history rather than a permanent structural difference alone. Titan's long seasonal cycle allows liquids to migrate and accumulate over time, so the present distribution may represent one phase of a larger climatic pattern. The liquid in these seas and lakes is not ordinary water. Under Titan's surface conditions, water ice is solid and rigid. While methane and ethane can be liquid, measurements and models indicate that the polar liquids are dominated by methane and ethane, with dissolved nitrogen and smaller amounts of other hydrocarbons likely present as well. Composition may vary from one body to another. Some lakes appear richer in methane, while others may contain larger fractions of ethane, especially where evaporation and atmospheric exchange differ, because methane is more volatile than ethane. A lake exposed to repeated evaporation can gradually change in composition. The liquid bodies are therefore chemically active reservoirs, not static pools of uniform material. Depth varies widely. Radar sounding has shown that some seas are very deep, in places descending hundreds of meters below the surface, while other lakes are much shallower. In some cases, the bottom can be detected by radar reflections. In others, the liquid is too deep or too absorptive for the signal to return from the floor. Shorelines can be steep in places and more gently sloping in others. The shapes of the basins suggest more than one formation process. Some appear consistent with erosion and drainage, where flowing liquids cut into the terrain and gather in topographic lows. Others, especially smaller and steeper-sided lakes, may involve dissolution, a process in which surface material is slowly removed by liquid, enlarging pits or depressions over time. On Titan, dissolution would involve hydrocarbons and organic-rich solids, rather than the water-based chemistry familiar from limestone landscapes on Earth. The surfaces of Titan's seas are generally very smooth. Wind-driven waves, if present, are usually small under the conditions measured during much of the Cassini mission. This smoothness is one reason the seas appear dark to radar. It also indicates that near-surface winds are often weak over the liquids, at least during many observations. Yet smooth does not mean inactive. Seasonal changes in temperature, wind, and composition can alter evaporation rates and may influence the appearance of shorelines or the formation of transient features. There have been observations of unusual bright patches or changing radar signatures in some sea regions, leading to discussion of bubbles, suspended solids, roughening by wind, or changing reflections. Some of these interpretations remain uncertain, and no single explanation has been established for every case. What is clear is that Titan's seas respond to environmental conditions and can change in measurable ways. The lakes and seas are central to Titan's methane cycle because they act as surface reservoirs. They store liquid hydrocarbons gathered from rainfall, runoff, and atmospheric transport. They also return methane to the atmosphere through evaporation. In this sense, they function somewhat like oceans and large lakes on Earth, though the analogy must be used carefully. Titan's seas are colder, composed of different molecules, and often situated in isolated basins rather than in one connected global ocean at the surface. Even so, they anchor the lower atmosphere to the ground by providing a persistent source and sink for volatile material. Shoreline forms reveal that liquids do not merely sit passively in place. Many lakes are connected to channel systems that enter or exit their basins. Some coastlines are sharply indented, suggesting long interaction between standing liquids and the terrain. Others appear smoother, perhaps shaped by sediment deposition, dissolution, or fluctuating liquid levels. Seasonal changes in volume may expose or flood marginal ground. Evidence from radar and topography indicates that some empty or partly filled basins also exist, showing that the balance between filling and drying can shift. Titan's polar regions are therefore landscapes of active exchange between atmosphere, liquid, and solid ground. There is also evidence that not all liquid movement is confined to the open surface. Some observations suggest communication between lakes and a porous subsurface, at least in limited areas. A porous material contains connected spaces through which liquid can move. On Titan, this could involve fractured ice or organic-rich sediments near the surface. Such exchange might help explain steep-walled lake basins, changing levels, or the absence of obvious surface channels in some places. The details remain uncertain, and the extent of subsurface liquid movement in the polar terrains is still under study. Even so, the possibility adds another layer to Titan's hydrologic style, one that links atmospheric and surface processes to shallow underground storage. The polar liquids matter scientifically for several reasons. They're direct evidence that Titan's climate is not hypothetical, but working now. They preserve information about atmospheric composition because gases dissolve differently in cold hydrocarbons. They interact with sediments and shoreline materials, creating natural laboratories for chemistry at low temperature. They may also record seasonal or longer-term climate shifts through changing levels and compositions. In addition, they demonstrate that stable surface liquids can exist far from the Sun when the right molecules and temperatures are present. This expands the known range of planetary environments capable of sustaining cycles between atmosphere and surface. In Titan's polar lakes and seas, the methane weather system becomes visible as stored geography. The atmosphere that once seemed only a veil above the moon now gathers at the ground in dark expanses bordered by icy and organic-rich land. These liquids are smooth, cold, chemically varied, and concentrated where climate and topography permit them to remain. They are not an incidental detail of Titan's poles. They are one of the clearest signs that this distant moon possesses an active surface world, one in which atmosphere, chemistry, and landscape meet in enduring reservoirs of liquid hydrocarbon. Beyond the standing liquids of the polar basins, Titan's surface shows many signs that methane rain and flowing liquid move across the ground in organized paths. These paths appear as channels, valleys, branching networks, and broad drainage systems that connect higher terrain to lower basins. They are among the clearest indications that Titan's climate is not limited to lakes and seas at the poles. It also reaches across land, carving, transporting, and reshaping the surface through the action of flowing hydrocarbons. On Earth, river systems reveal where water falls, where it gathers, and how it erodes rock and sediment over time. On Titan, the same general logic applies, but with methane and ethane acting under a dense, cold nitrogen atmosphere and over a crust in which water ice behaves like stone. The channel systems are observed mainly through radar imaging and topographic data, since Titan's visible haze blocks direct optical views of the surface. In these data, channels appear as dark, sinuous lines or branching patterns incised into brighter terrain. Some are short and local. Others extend for hundreds of kilometers and connect to larger liquid bodies. Their geometry is important. A dendritic network, meaning one that branches like the limbs of a tree, usually indicates runoff shaped by precipitation across a surface. Such patterns are difficult to explain by tectonic cracking alone because tectonic fractures often follow straighter, more systematic trends. The branching drainage on Titan therefore strongly supports the conclusion that rain falls and that liquid flows downhill across the land. Flowing liquid on Titan behaves differently from water on Earth in detail, yet not in principle. Gravity pulls the fluid downward. Surface slope guides its path. Erosion can remove material from the bed or banks, while sediment transport carries particles from one place to another. Sediment means loose, solid material moved by a fluid. On Titan, that material may include water ice grains, organic particles from atmospheric haze, and other hydrocarbon-rich deposits. The physical properties of methane and ethane differ from those of water. Their density, viscosity, and surface tension are not the same, especially in Titan's extreme cold. Even so, the landforms they create can still resemble terrestrial river systems because the governing mechanics of flow and erosion remain broadly similar. Some valleys on Titan are deeply incised, suggesting repeated or prolonged episodes of liquid movement. Others appear shallower and more braided, perhaps indicating sediment-rich flow or changing discharge over time. A braided channel is one in which flow divides and rejoins around bars or islands of deposited material. Whether a channel becomes single-threaded or braided depends on slope, sediment supply, bank strength, and the variability of flow. The presence of different styles on Titan suggests varied local conditions rather than one uniform process everywhere. In some places, the ground may resist erosion strongly because it is composed of rigid water ice. In others, loose organic sediments may be easier to move and reshape. Rainfall is a likely driver of many of these systems, especially in regions where channels begin far from present-day lakes and seas. If liquid appears on a slope where no standing surface reservoir exists nearby, precipitation becomes the most direct explanation. Observations of transient cloud systems and possible post-storm surface darkening support this interpretation. A wetting event can temporarily alter the reflectivity of the ground, making recently rained on regions stand out. Over long periods, repeated events would supply the runoff needed to cut valleys and feed basin networks. Titan's drainage patterns therefore preserve evidence of climate integrated over time, not just of isolated storms. The channels also reveal that topography matters. Liquid collects in lower ground, and flow converges where slopes direct it. Topographic measurements show regional highs and lows that help explain why some basins are richly fed, while others remain isolated. In the polar regions, drainage often leads toward lake districts and seas. At lower latitudes, Channels can terminate in alluvial fans or dry-looking basins, where liquids may have been more common under past climate conditions. An alluvial fan forms when a flowing liquid leaves a confined channel and spreads out, dropping sediment in a fan-shaped deposit. Features resembling such deposits have been proposed on Titan, suggesting that some flows lose energy and deposit their load when reaching flatter ground. Drainage networks also help constrain the mechanical nature of Titan's surface materials. A channel cut into hard ground implies a resistant substrate, while a wide shallow valley filled with depositional forms may indicate softer or more mobile sediments. Because water ice is as hard as rock under Titan conditions, it likely forms part of the structural framework in some terrains. Over that framework may lie layers of atmospheric organic particles, fluvial sediments, or evaporite-like deposits left behind when surface liquids recede. An evaporite is a material deposited as liquid evaporates and dissolved substances remain. On Titan, proposed evaporite regions may reflect compounds left after methane-rich liquids disappear. These materials would influence how runoff moves and where channels persist. Seasonality adds another dimension to drainage. Titan's long year means rainfall patterns can shift over many Earth years, and areas now relatively dry may not always have been so. Some equatorial and mid-latitude channels suggest that climates in the past may have supported more frequent precipitation there than is commonly observed in the present season. This does not require a radically different Titan. A slow migration of rainfall belts under seasonal and orbital forcing could gradually redistribute where the land is cut and where liquids collect. In this way, channels serve as records of both present and past methane activity. Not all channel-like features are simple to interpret. Some linear forms may arise from tectonic processes, collapse, or the modification of older structures by later flow. Radar images can also be ambiguous where resolution is limited, yet taken together. The widespread occurrence of branching valleys, integrated drainage, basin connections, and polar inflow systems leaves little doubt that flowing liquid has shaped Titan on a large scale. The surface is not only coated by atmospheric organics and punctuated by standing seas, it is traversed by routes of transport that connect climate to terrain, in Titan's rivers, valleys, and drainage systems. Motion replaces stillness. The methane that evaporates from lakes condenses in the air and falls as rain does not vanish when it reaches the ground. It travels. It gathers into channels, cuts slopes, carries sediments, fills depressions, and feeds larger reservoirs. Through these pathways, Titan's climate writes itself into the landscape. The moon's surface becomes legible as a network of movement, one where the cold chemistry of hydrocarbons takes on a familiar physical form, the organized descent of liquid across land, away from the polar lake district and their dense networks of channels. Titan's equatorial regions present a different kind of surface system. Here, broad plains are shaped not primarily by standing liquids, but by wind. Across thousands of kilometers, long parallel ridges form immense dune fields, giving Titan one of the largest known expanses of dunes in the solar system. These dunes are not small ripples. They are large linear structures, often hundreds of meters high and extending for many kilometers, arranged in patterns that suggest persistent winds acting over long spans of time. Their scale and coherence reveal that Titan's atmosphere, despite its dim sunlight and cold temperature, is capable of moving solid material across the surface and organizing it into stable forms. The dunes are observed most clearly in radar images. In such images, dune fields appear as dark, uniform regions with regular linear texture. The darkness is partly a matter of radar interaction with surface roughness and material composition. Smooth surfaces that reflect radar away appear dark, while rougher or differently structured surfaces scatter radar back and appear brighter. Dune sands and their arrangement can therefore have characteristic radar signatures. The linear dunes on Titan are oriented in a way that indicates dominant wind directions over time. They are often aligned roughly east to west, though local variations occur. Their shape suggests winds that alternately blow from different directions, producing net sand transport along a stable axis. The sand on Titan is not made of silicate rock grains like desert sand on Earth. Under Titan's conditions, water ice is very hard, but it is also less dense than many organic solids. Many researchers infer that Titan's dune grains are likely organic in nature, derived ultimately from atmospheric chemistry. The haze particles that settle out of the atmosphere provide a steady supply of carbon-rich material to the surface. Over time, this material can accumulate, be processed by weathering, and be broken into grains that wines can move. Another possibility is that some grains include water ice fragments coated with organics, or mixtures of organic and icy material. The exact composition and mechanical properties remain an area of study. What is clear is that the dunes represent a long-term integration of atmospheric production, surface processing, and aeolian transport. Aeolian means shaped by wind. Moving grains across a surface requires winds strong enough to overcome friction and cohesion between particles. Titan's dense atmosphere helps, even though winds near the ground can be modest in speed. The density of the air means it can exert significant force on grains. Titan's low gravity also reduces the weight pressing grains into the ground. Together, these factors lower the wind speed threshold needed to lift and move particles compared with a thin atmosphere. Even so, Titan's winds are not constant. They vary with season and with atmospheric circulation. The large-scale dune patterns suggest that strong gusts or episodic events may play a role, perhaps linked to seasonal changes or storm systems. The dunes preserve the cumulative outcome, not the details of each transport episode. The dunes also interact with topography. They occur in broad belts around the equator, often occupying lowlands and wrapping around obstacles. Where mountains or high ridges interrupt the plains, dune orientations can bend and adjust, indicating that local airflow influences their shape. In some places, interdune regions, the areas between dune ridges, appear brighter in radar, suggesting different surface materials or rougher ground. These areas may be exposed bedrock of water ice, older sediments, or hardened deposits that resist wind movement. The dunes themselves migrate slowly, reshaped by each episode of transport. Yet their overall fields can remain stable in location for long spans if the supply of sand and wind regime persists. The equatorial dune fields matter for understanding Titan's climate because they point to persistent atmospheric circulation patterns. A world without strong or consistent wind organization would not produce dunes of such uniform scale and alignment. Titan's dunes indicate that the lower atmosphere not only supports methane weather in certain regions, but also maintains a global wind system capable of moving solids. This links the equator to the poles in a broader atmospheric context. Methane may concentrate in polar reservoirs, while organic solids and sediments may be concentrated and sorted at lower latitudes by wind. This surface therefore becomes partitioned by climate processes, with different latitudes dominated by different forms of transport. There are also signs that dunes are not isolated from liquid processes. Some dune fields show evidence of channels crossing them, or of disruptions that suggest occasional wetting events. Methane rain in equatorial regions may be less frequent than at higher latitudes during some seasonal intervals, but it likely occurs over longer timescales. When rain falls on dunes, it can alter grain cohesion and temporarily change how wind moves material. It can also create crusts when liquid evaporates and leaves behind deposits. Such interactions are complex, and the available data do not always allow a single interpretation. Yet the presence of both aeolian and fluvial features in some regions indicates that Titan's surface processes overlap rather than divide into fully separate domains. The dunes also provide clues to the nature of Titan's surface materials in general. On Mars, dunes and dust reveal a surface dominated by silicate fragments. On Titan, dunes point toward a surface where carbon-based solids are abundant and mobile. This makes Titan an important comparative world for understanding how organic matter behaves on planetary surfaces. It also provides a natural test of sediment transport in conditions very different from Earth, including low temperature, dense nitrogen air, and reduced gravity. Such comparisons help refine general models of landscape formation that can be applied across worlds. In the equatorial plains, Titan appears as a planet of sand, though the word sand here refers to grain size and mobility rather than to mineral composition. Ridges extend in long-ordered lines, built by winds that operate under dim light and cold air. The dunes stand as the surface expression of atmospheric motion acting on organic deposits created overhead. They show that Titan's atmosphere is not only a chemical factory and a driver of methane storms, it is also a shaping force that can sculpt wide regions into repeating patterns. In these dunes, Titan's surface becomes a record of slow, persistent wind, carrying the products of sky chemistry across the ground and arranging them into vast, silent fields. Beyond the broad equatorial dune seas, Titan's surface rises into rougher terrains where the ground appears brighter in radar and more varied in texture. These regions include uplands, ridges, and terrains marked by impact craters. They provide a different kind of record from the dunes. Dunes mostly record transport and sorting of mobile grains under wind. Highlands and cratered terrains record structural strength, long-term exposure, and the history of impacts and erosion. In these areas, Titan's surface is more clearly anchored to its bedrock, meaning the underlying solid framework that supports sediments and shapes relief. Under Titan's surface conditions, the primary bedrock is water ice. At roughly 94 degrees Kelvin, water ice is rigid and strong, behaving in many ways like silicate rock on Earth. It can fracture, support cliffs, and preserve topographic forms over long spans. It can also creep slowly under its own weight, especially if warmed or mixed with other materials. But the key point is that it provides a solid foundation. Above it, layers of organic deposits and transported sediments may accumulate, yet the highlands often expose more resistant material or have thinner coverings. This is one reason they appear brighter in some radar views. Rougher, more fractured surfaces tend to scatter radar more strongly. Titan's highlands are not concentrated in one simple belt. They occur in multiple regions, including areas near the equator and in mid-latitudes. Some are described as mountainous terrain because of their rugged relief. Others are more subdued, with rolling topography. Their origins likely include tectonic processes, meaning deformation of the crust by stress, as well as erosion and deposition. Titan does not display the same style of plate tectonics seen on Earth, and there is no evidence of mobile crustal plates exchanging material through subduction in the terrestrial sense. Instead, Titan's tectonic shaping likely involves broad bending, faulting, and localized uplift within an icy shell. The details remain an area of active research, but the presence of ridges and elevated blocks suggests that internal forces have contributed to shaping the crust. Impact craters provide a separate and powerful diagnostic. A crater forms when a cosmic object strikes the surface at high speed, releasing energy that excavates material and leaves a circular depression, often with raised rims and sometimes central peaks. On Titan, craters are comparatively rare in the regions observed at high resolution. This scarcity suggests that the surface is relatively young in geologic terms, or that resurfacing processes remove crater traces over time, or both. Resurfacing can occur through erosion, sediment deposition, dissolution, or internal activity. Titan has active atmospheric and surface processes capable of altering landforms. Dunes can bury craters, liquids can erode rims, and deposits can fill depressions. The relatively low crater density therefore supports the idea that Titan's surface is dynamic and continually modified. Where craters are seen, they reveal how materials behave. The rims and ejecta, meaning material thrown outward by the impact, can appear brighter in radar, suggesting roughness and fractured ice. Some craters show dark floors that may be filled with sediments or organic deposits. Others have signs of erosion along their rims. The crater called Selk, for example, has been studied as a potential landing region for future exploration, because it may expose materials altered by impact heating and later modified by Titan's environment. Impact sites can briefly melt or warm ice and can drive chemical changes, creating environments distinct from the surrounding cold plains. Even after cooling, they remain places where different materials may be exposed or concentrated. Erosion in the highlands occurs through more than one pathway. Methane rainfall and runoff can carve valleys that cut into elevated terrain, transporting sediments downhill. Wind can abrade exposed surfaces, though abrasion by wind-driven grains depends on the availability of mobile material and on wind strength. Dissolution can also play a role, especially if surface materials include soluble organics that can be gradually removed by contact with liquid hydrocarbons. These processes act slowly, yet over long spans they can lower ridges, smooth scarps, and feed sediments into adjacent basins and dune fields. Highlands therefore contribute material to lower regions. They are not isolated. They are sources within a broader system of transport. The contrast between bright, rugged uplands and dark, smooth dune seas also indicates differences in composition or surface texture. Radar brightness depends on both. A rough surface with facets at many angles returns more signal. A smoother surface reflects signal away. Composition matters because different materials have different dielectric properties, meaning they interact with electromagnetic waves in distinct ways. Water ice and organic solids can differ in this respect. Interpreting radar brightness therefore requires careful analysis, and multiple explanations can be consistent with the same image. Even so, when combined with topography and other data, the pattern supports a view of Titan where resistant icy highlands stand above softer or more mobile sediments in the lowlands. These terrains offer a partial analogue to Martian highlands and cratered plains, yet the comparison has limits. Mars preserves a long record of impact history and volcanic resurfacing in its ancient cratered terrains. Titan's crater record appears more incomplete, not because impacts did not occur, but because active surface processes and possibly internal activity have modified or erased many traces. This makes Titan valuable in a different way. It shows how an atmosphere and a surface liquid cycle can reshape a world enough to obscure parts of its impact history, even in a cold environment far from the sun. In the ice highlands and cratered regions, Titan's surface becomes a record of strength and change. Water ice acts as rock, holding relief and forming the underlying crust. Impacts puncture this crust and expose fresh materials, while erosion and deposition slowly rewrite the scars. These terrains balance persistence and alteration. They are durable enough to stand above surrounding plains, yet they are not immune to the long work of methane rain, sediment transport, and wind. In this balance, Titan displays a kind of geology that is neither purely frozen and static nor fully Earth-like. It is the geology of a cold world with an active atmosphere, where bedrock and climate meet in rough uplands and in the rare, telling circles of craters. Among Titan's rough terrains and varied surface patterns, some regions have drawn special attention because they may preserve evidence of cryovolcanism. Cryovolcanism means the eruption or extrusion of volatile rich material, such as water mixed with ammonia or other compounds, under temperatures so low that ordinary rock melting is not required. On a world like Titan, where surface water ice is rigid and where internal heat may still exist beneath the crust, cryovolcanism would be a way for subsurface material to reach or approach the surface. The idea is scientifically important because it could connect the hidden interior to the visible landscape and perhaps help replenish atmospheric methane over long spans. Yet the evidence is not straightforward. Titan's haze, limited resolution, and the complexity of its surface processes make interpretation difficult. For this reason, possible cryovolcanic terrains must be described with care. Several features have been proposed as candidates. One of the most discussed is Sotra Patera, a region that includes deep depressions, elevated relief, and flow-like patterns in radar and topographic data. A patera is a broad, irregular volcanic depression in planetary terminology, though the term does not prove volcanic origin by itself. The shape of Sotra Patera and the nearby mountainous blocks led some researchers to suggest a cryovolcanic interpretation, perhaps involving uplift, collapse, and the outpouring of icy material. Other regions, such as Doom Mons and Erebor Mons, have also been considered in this context because of their apparent topography and association with unusual surrounding terrains. These names identify places of interest, but they do not settle the question of process. A cryovolcanic landscape on Titan would not look exactly like lava fields on Earth. If water-rich material, possibly mixed with ammonia or dissolved gases, rose from the interior and reached the cold surface, it could freeze rapidly, deform slowly, or spread in lobate forms depending on its composition and temperature. Ammonia lowers the freezing point of water, making liquid phases more feasible in the interior. Dissolved methane or other volatiles might also be released during ascent or emplacement. In principle, this could create domes, flows, pits, or collapse structures. In practice, however, some of these same forms can arise through non-volcanic processes such as tectonic deformation, erosion, sedimentary accumulation, or impact-related modification. This is why proposed cryovolcanic sites remain debated. One reason cryovolcanism is considered plausible is Titan's internal structure. Measurements of gravity, shape, and rotation strongly support the presence of a deep subsurface ocean beneath the ice crust. If an ocean exists, then internal materials are available that could, under some conditions, migrate upward. Tidal forces from Saturn may provide some internal heating, and radioactive decay within the rocky core can contribute heat over long spans. These sources are not expected to drive intense or widespread activity comparable to major silicate volcanism on Earth, but they may be sufficient to maintain localized movement within the ice shell or occasional ascent of buoyant liquids. The question is not whether Titan has the materials for cryovolcanism in theory. It is whether the observed surface landforms require that explanation. Methane adds further interest. Titan's atmosphere contains methane now, yet methane is destroyed gradually by photochemical reactions in the upper atmosphere. Over geologic time, this means methane must be resupplied or Titan would lose its present atmospheric abundance. One proposed source is release from the interior, either through cryovolcanic eruptions or through more diffuse pathways such as fractures and slow seepage. This idea is plausible, but it remains uncertain. Surface and shallow subsurface reservoirs may also store methane, and episodic release need not always produce dramatic volcanic landforms. Therefore, while cryovolcanism is one candidate mechanism for methane replenishment, the current evidence does not establish it as the only or dominant source. Observationally, the challenge lies in ambiguity. Radar images can show lobate margins, rough textures, or elevated structures suggestive of flows or domes, but similar appearances can arise in other ways. Topography can reveal depressions and rises, yet without direct sampling it is difficult to determine whether a raised region is a cryovolcanic edifice, a tectonic block, or an erosional remnant. Infrared observations provide additional clues about composition, but Titan's haze and the limited transparency windows constrain what can be seen. The available data are rich enough to identify unusual terrains, though not always sufficient to assign a single confident origin. There is also the problem of preservation. If cryovolcanic activity occurred long ago, later erosion by methane rain, burial by dunes or atmospheric deposits, and tectonic deformation may have altered or obscured the original forms. A surface shaped by multiple processes can retain partial signatures that no longer fit neatly into one category. Titan is especially prone to this difficulty because its atmosphere and active surface cycle continually modify the landscape. As a result, some terrains may be ancient cryovolcanic candidates that have been overprinted by younger processes, while others may be entirely non-volcanic features that happen to resemble volcanic forms. Laboratory and theoretical work help frame the possibilities. Models of icy shell dynamics examine whether buoyant plumes, fracture pathways, or localized melting could deliver liquid or slushy material upward. Experiments on water-ammonia mixtures and organic-rich ices constrain how such materials would behave under Titan conditions. These studies show that cryovolcanic processes are physically possible, but possibility is not proof of occurrence at any given site. Planetary science often advances through this difference between what a world can do and what it demonstrably has done. In these possible cryovolcanic terrains, Titan presents one of its most intriguing uncertainties. The surface hints that internal materials may at times approach the outer world, perhaps in raised constructs, irregular depressions, and flow-like deposits. Yet the evidence remains open to multiple readings. Observations indicate unusual landscapes and an interior capable of supplying volatile-rich material. It remains uncertain whether the most prominent candidate regions are best explained by cryovolcanic emplacement, tectonic reshaping, erosion, or some combination of these processes. This uncertainty is itself scientifically valuable. It shows that Titan is not fully understood at the boundary between surface and interior, and that this boundary may hold some of the keys to why the Moon remains chemically and geologically active. Across Titan's surface, beneath the dunes and around the margins of lakes and channels, a widespread layer of carbon-rich material is expected to accumulate from the atmosphere. This layer is not a single uniform coating, but a complex mixture of solids and ices shaped by deposition, transport, wetting, and slow chemical change. Titan's atmosphere produces organic molecules continuously in the upper layers, and many of these products ultimately descend as haze particles. Over time, this creates a steady delivery of complex organics to the ground. Once on the surface, these organics become part of a landscape chemistry that is unlike that of Mars and unlike that of Earth, because it occurs at extremely low temperature, in contact with liquid hydrocarbons rather than liquid water, and under a nitrogen sky. The organic material reaching the surface begins as tiny aerosol particles formed aloft. As they settle, they can clump, gain coatings, and become embedded in other deposits. When they arrive at the ground, they may mix with water ice grains, become compacted by time, or be reworked by wind and methane rainfall. In dune fields, organic grains may form the bulk of the sand. In lake districts, organic solids may settle in shore zones or be carried by runoff into basins. In highlands, atmospheric organics may drape rough ice bedrock, filling small depressions and smoothing some surfaces. This continuous fall of particles means that Titan's surface chemistry is fed from above in a persistent way. At Titan's temperatures, many chemical reactions that proceed rapidly on Earth become extremely slow. Low temperature reduces molecular motion and can limit reaction rates. Yet chemistry does not stop. It shifts. Some reactions can still occur through slow diffusion, through radiation-driven processes, or through catalytic effects on surfaces. Energetic particles and ultraviolet light are weaker at the surface than aloft because of shielding by the haze and atmosphere. But some energetic input still arrives. Cosmic rays can penetrate and deposit energy in the ground. Secondary particles and radiation products can drive chemical change in surface materials. Over long spans, these energy sources may gradually alter organic solids, changing their structure and producing new compounds. Titan's liquid hydrocarbons add another set of processes. Methane and ethane can dissolve certain organic molecules. A liquid can act as a solvent, meaning it can carry dissolved substances and transport them. On Earth, water dissolves salts and many organic compounds, enabling strong chemical cycling. On Titan, methane and ethane are less effective solvents for many polar molecules, meaning molecules with uneven charge distribution, yet they can still dissolve some organics and can mobilize them through flow. When rain falls and runs off, it can pick up soluble or suspendable material and carry it into channels and basins. When lake levels change, dissolved substances can be left behind as deposits. This creates the possibility of evaporate-like materials on Titan, though the compounds involved would differ greatly from terrestrial evaporates. Observations support the presence of compositionally distinct surface units. Certain bright and dark regions in infrared and radar data appear consistent with differences in material properties. Some terrains around lake margins show spectral signatures consistent with deposits left by receding liquids. These areas have been proposed as evaporate candidates, possibly composed of organic solids precipitated from hydrocarbon solutions. The exact identity of these solids remains uncertain because remote sensing cannot uniquely identify all complex mixtures, and because laboratory spectra for Titan-relevant materials are still being refined, observations indicate distinctive deposits. It remains uncertain which specific compounds dominate them and how uniform they are across different basins. Surface chemistry also interacts with water ice. Water ice is abundant in Titan's crust, yet at the surface it remains frozen and does not behave like liquid water. Even so, water ice provides surfaces for adsorption, meaning molecules can stick to solid surfaces. It can also trap organics in pores and fractures. Where impacts occur, local heating can briefly alter ice, potentially allowing limited melting or chemical rearrangement before the environment cools again. Such events could create localized mixtures of water and organics, at least temporarily. Though how long such conditions could persist depends on the size of the heated region and the insulating effects of surrounding materials. These are special cases rather than the norm, yet they matter because they expand the range of chemical environments present on Titan's surface. The scale of organic deposition across Titan has broad implications. Over very long spans, the mass of carbon-rich material delivered from the atmosphere could become substantial, potentially forming thick layers in lowlands or basins. The distribution would not be uniform because winds, rainfall, and topography sort and relocate materials. Dunes concentrate grains in equatorial belts. Lakes gather dissolved and suspended material in polar basins. Channels connect highlands to lowlands, delivering sediments and organics across terrain boundaries. In this way, Titan's surface chemistry becomes inseparable from its surface geology. Chemical products become sediments. Sediments become landscapes. Landscapes then control where liquids and winds move next. This integrated system is one reason Titan can be argued to rival Mars in scientific importance, though the comparison must be framed carefully. Mars offers direct access to a rocky surface with a history of liquid water in the distant past and a thin present atmosphere. Titan offers an active present cycle involving hydrocarbons and a thick nitrogen atmosphere. Titan also offers an ongoing planetary scale factory of complex organic chemistry. The chemical richness is not a minor trace. It is a defining feature of the environment. Studying it helps constrain how organic molecules form and evolve in planetary atmospheres, and how they interact with surfaces under conditions far from those of Earth. Yet the limits are as important as the richness. Titan's surface is extremely cold, and liquid water is not stable there. The chemistry that occurs at the surface is therefore not a direct analogue of the chemistry that supports life on Earth today. Organic molecules can form and accumulate without biology, and Titan demonstrates this clearly. The scientific value lies in understanding pathways of organic synthesis and transformation under planetary conditions, not in assuming any particular biological outcome. Observations indicate complex organics are abundant and mobile. It remains uncertain how far chemical complexity can progress in the surface and near-surface environment without episodes of warmer conditions or interaction with liquid water. In this region of surface chemistry and organics, Titan becomes a world where atmosphere, liquid hydrocarbons, and solid deposits form a continuous chemical cycle. The haze that begins high above becomes material on the ground. Rain and rivers move that material. Lakes and seas dissolve and concentrate it. Radiation and time alter it. The surface is therefore not only sculpted by wind and liquid flow, but also composed of substances that carry a long chemical history from the upper air down to the landscape. In that history, Titan offers a rare view of organic matter evolving in a planetary setting, with processes operating now in slow, steady motion under a cold, dense sky. Beneath Titan's active surface lies the outer shell of the Moon itself, a crust composed primarily of water ice mixed to varying degrees with other materials. This crust is not a thin frost or a simple frozen skin. It is a planetary scale shell that supports mountains, basins, dunes, river valleys, and polar seas, while also separating the visible surface from the deeper interior. Under Titan's surface temperatures, water ice is mechanically strong, yet its behaviour changes with depth. Near the top it acts as a cold, rigid solid. Farther down, where pressure rises and temperatures increase, ice can deform slowly over long times. The crust must therefore be understood not as a single uniform layer, but as a structure whose properties vary inward. The uppermost part of the crust forms the bedrock of Titan's landscapes. In highlands and cratered terrains, it likely approaches the surface directly, or lies beneath only a shallow cover of sediments and atmospheric organics. In dune fields and polar basins, it may be buried beneath mobile grains, liquid carved deposits, or layered chemical residues. Even where hidden, however, the crust sets the broad topography. It supports elevation differences and helps determine where lakes collect, where channels incise, and how tectonic stresses are expressed. Because Titan's gravity is lower than Earth's, topography can be supported somewhat differently. Yet the rigid near-surface shell still bears the weight of overlying materials and resists deformation over ordinary timescales. Evidence for the crust structure comes from several lines of observation. Gravity measurements show how mass is distributed inside Titan. Shape measurements indicate how the Moon responds to rotation and tides. Radar and topographic mapping show the scale and style of surface relief. Taken together, these observations indicate that Titan's outer shell is mechanically decoupled in some way from the deep interior, strongly implying that a liquid layer exists below. That conclusion belongs to the next, deeper region. At the level of the crust itself, the important point is that the ice shell is not fixed to the entire Moon as one rigid body. It behaves as the outer solid envelope above a more mobile interior. Thickness is more difficult to determine. Models based on gravity, topography, and thermal structure suggest that Titan's ice shell may be tens of kilometers thick, and possibly more in some scenarios, but exact values remain uncertain. The shell may also vary in thickness from place to place. Regions with different heat flow, composition, or internal stress could develop different crustal properties. An ice shell containing ammonia, salts, clathrates, or embedded rocky material would not behave exactly like pure water ice. A clathrate is a solid in which one kind of molecule is trapped inside a lattice of another, and such materials may matter in icy worlds because they affect density and thermal behavior. These compositional details are important because they influence how easily the crust fractures, how it insulates the interior, and how fluids might move within or through it. Tectonic features on Titan suggest that the crust has been stressed and deformed. Radar images reveal lineaments, ridges, and disrupted terrains in several regions. A lineament is a long linear surface feature that may reflect faulting, fracturing, or structural weakness. Some of Titan's linear features may result from global contraction or expansion, while others may arise from local forces, tidal stresses, or differential loading by sediments and liquids. The exact causes differ by region and are not always easy to identify. Still, the existence of these structures shows that Titan's crust is not a passive, unchanging shell. It has been bent, fractured, and altered by internal and surface processes alike. The crust also participates in thermal control. Heat from the interior must pass outward through it. A thicker or more insulating shell slows that transfer, helping preserve a subsurface ocean beneath. A thinner or more fractured shell could allow greater local heat flow and perhaps support features sometimes interpreted as cryovolcanic or tectonically active terrains. The crust therefore acts as both barrier and regulator. It keeps the surface cold enough for methane and ethane to remain stable as liquids in some places, while also retaining enough internal heat below to prevent the entire interior water inventory from freezing solid. Mechanical layering within the crust is likely. The shallow part is cold and brittle, meaning it tends to fracture when stressed. Deeper down, where temperatures are higher, ice may become ductile, meaning it deforms gradually without breaking. The boundary between brittle and ductile behavior affects how faults form and how topography relaxes over time. A crater or ridge preserved for long intervals implies that the relevant depth range has remained strong enough to resist complete smoothing. Conversely, the partial relaxation of some topographic forms may indicate that deeper ice can flow slowly under load. This combination of rigid upper shell and weaker lower shell is common in planetary bodies with icy crusts, and Titan appears consistent with that general pattern. The crust may also interact with shallow liquids or porous materials near the surface. In polar regions, some lakes may communicate with local subsurface spaces through fractures or porous deposits. In impact zones, the crust may be shattered and mixed with organic sediments. In dune-covered lowlands, the crust may be hidden beneath thick surface materials. These interactions do not change the fundamental identity of the crust as Titan's outer solid shell, but they do make its boundary with the surface irregular and dynamic rather than perfectly sharp. From a scientific perspective, Titan's crust is crucial because it records both outward and inward influences. From above, it is sculpted by atmosphere, rain, liquids, and wind. From below, it responds to internal heat, tidal stress, and the properties of the deeper ocean and rocky interior. It is the meeting layer where climate leaves lasting marks, and where interior dynamics may occasionally approach the surface. This dual role makes Titan's crust especially important in comparison with Mars. Mars has a rocky crust that preserves ancient water-related landforms and volcanic provinces. Titan's crust is icy, mechanically different, and tied directly to an active present climate of hydrocarbons. Each world offers a distinct archive. Titan's archive is written in frozen water rock under a thick atmosphere. In the ice crust, Titan becomes structurally coherent as a world. The dunes, channels, lakes, and highlands above it are no longer isolated features. They rest on a shell that supports them, deforms under stress, insulates the hidden interior, and preserves the surface record in forms both rugged and subtle. The crust is strong yet not immutable, cold yet not inert, and central to the moon's identity as an active icy body. It is the frozen framework beneath the climate-shaped surface, and the final solid barrier before Titan opens into deeper and more concealed layers below Titan's ice crust. Evidence strongly supports the presence of a global subsurface ocean, a layer of liquid water separated from the surface by tens of kilometers of ice. This ocean is not directly seen, yet its existence is inferred from multiple consistent observations of Titan's gravity field, shape, and response to tidal forces. A tidal force is the changing pull exerted by Saturn as Titan moves through its orbit. Even though Titan's orbit is close to circular, Saturn's gravity still produces tides that can flex the Moon slightly. If Titan were solid all the way through, its outer shape and gravity response would follow one pattern. Measurements instead indicate a response more consistent with an outer shell that is at least partly decoupled from the deeper interior by a liquid layer. In this way, the ocean is detected not by sight, but by the physics of how the Moon moves and how its mass is arranged. The ocean's composition is likely water-rich, but it may not be pure water. At Titan's interior pressures and temperatures, salts and ammonia can remain dissolved and can lower the freezing point. Ammonia is of special interest because it can make liquid water stable at lower temperatures than pure water would allow. This matters for a distant world where internal heat is limited compared with that of rocky planets. The presence of ammonia or salts would also change the ocean's density and electrical properties. Some analyses suggest that the ocean could be a water-ammonia mixture, while others allow for different dissolved components. The exact composition remains uncertain because it depends on Titan's formation history, the composition of its building materials, and the long-term evolution of its interior. The ocean's depth and thickness are also uncertain. Models suggest a substantial global layer, possibly hundreds of kilometers thick, but values depend on assumptions about the crust thickness above and the size and density of deeper layers below. Gravity data and Titan's moment of inertia, a measure of how mass is distributed with depth, constrain possible interior structures, yet they do not yield a single unique solution. Observations indicate an ocean exists and likely extends globally. It remains uncertain how thick it is in different regions and how its properties vary with location. The ocean is important because it represents a large reservoir of liquid water in a place where surface water is locked as ice. On Earth, liquid water at the surface supports a rich range of chemical environments. On Titan, liquid water at the surface is not stable, but a subsurface ocean provides a potential environment for water-based chemistry. This does not imply any biological outcome. It simply establishes that Titan, like several other icy worlds, contains liquid water beneath ice. The scientific significance lies in understanding how such oceans form, persist, and interact with their surroundings. Interaction between the ocean and the ice shell above depends on heat flow and on the mechanical behavior of ice. Heat from below can cause slow convection within the ice shell. Convection is the movement of material driven by buoyancy differences, often caused by temperature gradients. If warmer, slightly less dense ice rises while cooler, denser ice sinks, the shell can circulate over long time scales. This circulation can transport heat and may also transport chemical components, especially if brines or ammonia-rich melts are involved. Whether Titan's ice shell convects strongly or remains mostly conductive, meaning it transfers heat mainly through slow diffusion, is an open question. Observations indicate a shell thick enough to insulate and strong enough to support surface features, while still allowing an ocean beneath. It remains uncertain which internal heat transport regime dominates. The ocean may also be stratified, meaning it could contain layers with different composition or temperature. Denser salt-rich water could sink, while fresher water could remain above, depending on the mixture. Such layering would influence how the ocean circulates, how it transports heat, and how it exchanges chemicals with the overlying ice. The ability of the ocean to mix depends on heating, rotation, and the presence of compositional gradients. These processes are challenging to constrain with present data, yet even without detailed knowledge of circulation, the simple existence of a stable liquid layer changes the meaning of Titan as a planetary body. One of the most important questions is the degree of exchange between the ocean and the surface. The thick ice shell is a barrier. It prevents easy contact between the ocean and the surface environment of hydrocarbons and organics. However, barriers can be imperfect. Fractures, localized thinning, or episodes of partial melting could allow limited transport of water or dissolved materials upward. Conversely, surface organics could potentially be carried downward through cracks, impact-induced mixing, or slow burial and recycling of ice. The extent of such exchange remains uncertain. Observations indicate a deep separation between surface and ocean. It remains uncertain how often and how efficiently that separation is bridged over geologic time. This ocean bears directly on Titan's broader scientific importance. Mars is a rocky planet with strong evidence for liquid water on its surface in the distant past, and for ice and brines today in limited forms. Titan is a moon with present-day surface liquids, but those liquids are hydrocarbons, not water. The subsurface ocean provides Titan with water in liquid form, but hidden. This combination is rare. It means Titan can host two distinct liquid regimes in one world: hydrocarbons at the surface and water below. The boundary between them is an ice shell that may store and modify materials passing through it. This arrangement creates a layered laboratory for chemistry, climate, and interior physics. Understanding Titan's ocean also informs the study of other icy worlds. Similar subsurface oceans are inferred at Europa, Enceladus, Ganymede, and possibly other bodies. Each world differs in heat sources, shell thickness, and surface conditions. Titan's uniqueness lies in its thick atmosphere and active surface hydrocarbon cycle. The ocean adds a deep interior context to that surface activity. It turns Titan into a world where atmosphere and surface processes occur above an interior that may still be chemically and physically dynamic. In this hidden ocean, Titan's inward path reaches a liquid layer that is central yet concealed. The surface above remains cold enough for methane rains and hydrocarbon seas, while below, water may remain liquid under pressure and with the help of dissolved compounds that depress freezing. Observations indicate a global ocean and a shell that moves in response to tides in ways consistent with a decoupled interior. It remains uncertain how the ocean circulates, what its full composition is, and how often it exchanges material with the surface. Even with these uncertainties, the ocean establishes Titan as more than an atmospheric and surface curiosity. It is a layered world with a deep liquid interior, adding a powerful dimension to its role as one of the most scientifically compelling targets in the outer solar system. Below Titan's subsurface ocean, the Moon's interior continues inward into denser layers where ice gives way to rock, and the deeper structure determines the long-term thermal and chemical evolution of the entire world. The deepest interior is not accessible to direct observation, yet it is constrained by Titan's bulk density, gravity field, and rotational behavior. These constraints indicate that Titan contains a significant rocky component beneath its water-rich layers. The rocky interior holds most of the Moon's mass and carries the long-lived sources of internal heat that come from radioactive decay. This deep heat is modest compared with that of a larger rocky planet, yet over billions of years it can be sufficient to maintain an ocean and to drive slow internal processes that influence what happens above. The transition from the ocean into the deeper interior likely involves high-pressure forms of ice, depending on pressure and temperature conditions. Water has multiple solid phases, meaning different crystalline structures that become stable at different pressures and temperatures. Under high pressure, ice can adopt forms denser than ordinary ice found at Earth's surface. In many models of icy moons, a layer of high-pressure ice can form beneath an ocean, separating the ocean from the rocky core. Whether Titan has such a layer depends on the depth of the ocean, the temperature profile, and the overall interior structure. Some models allow the ocean to lie directly on rock. Others place high-pressure ice between. Observations indicate Titan has a water-rich outer portion and a rocky interior. It remains uncertain whether high-pressure ice separates the ocean from rock everywhere or whether contact occurs in some regions. Contact matters because rock-water interaction can produce chemical energy. When liquid water interacts with certain minerals, It can drive reactions that release heat or create chemical gradients. On Earth, similar processes occur in hydrothermal systems. On Titan, if the ocean contacts rock, reactions could alter ocean composition, supply dissolved ions, and change the ocean's chemistry over time. If high-pressure ice blocks contact, exchange would be reduced, and chemistry would be shaped more by initial composition and by processes within the ice shell. Present data do not resolve this in detail, so the role of rock-water interaction remains an open component of Titan's internal story. The rocky interior also affects Titan's methane history. Methane observed in Titan's atmosphere today is continuously broken down by sunlight in the upper atmosphere. Over very long spans, methane must therefore be replenished, stored, or periodically resupplied. One possible long-term source is production within the interior, either through chemical reactions involving carbon-bearing materials in the rock, or through release of methane trapped during Titan's formation and later stored in clathrates within the ice shell. A clathrate can trap methane in a water ice lattice, creating a stable storage form under certain pressures and temperatures. If conditions change, methane can be released. Observations indicate methane is present, and that Titan's climate cycles it actively at the surface. It remains uncertain what combination of interior production, stored reservoirs, and episodic release maintains the long-term methane budget. The deep interior influences surface conditions mainly through heat flow and through the way it shapes the thickness and behavior of the ice shell. A warmer interior favors a thinner or more deformable shell. A cooler interior favors a thicker, more rigid shell. These differences can alter the likelihood of fractures, the possibility of localized melting, and the rate at which the surface relaxes or renews. Titan's surface appears to be geologically young in many places, with limited crater preservation and extensive signs of active reshaping by wind and liquids. Some resurfacing is purely atmospheric and sedimentary, but internal structure sets the boundary conditions. A world with no internal heat would eventually become more rigid and less able to adjust. Titan appears to retain enough internal energy to keep an ocean and to allow structural evolution, even if surface change is dominated by climate. Titan's importance relative to Mars becomes clearest when the whole layered system is viewed as a set of distinct scientific laboratories stacked within one world. Mars is a rocky planet close enough to the Sun that surface water could exist in the past, and where present conditions preserve mineral and sediment records of ancient environments. Mars is central to questions about early planetary habitability in a water-rich era, and about the history of atmospheres on terrestrial planets. Titan, in contrast, is a present-day laboratory for atmospheric chemistry and climate under a thick nitrogen sky, with an active cycle of hydrocarbons at the surface and a water ocean hidden below. Titan demonstrates that complex organic chemistry can operate on a planetary scale without biology and without surface liquid water, producing aerosols, deposits, and varied molecules that are transported through weather and sediment systems. This addresses questions about how organic matter forms and evolves in planetary environments, a subject that reaches beyond the solar system into the interpretation of hazy exoplanets and cold worlds. Titan also offers a rare chance to study a stable surface liquid system that is not water-based. The polar seas provide real shorelines, real basins, and real liquid exchange with the atmosphere. The equatorial dunes show atmospheric sorting of organic sediments. River networks show that rainfall and runoff can cut landscapes at extremely low temperature. These processes are occurring in the present epoch, not only inferred from ancient rock, Mars provides ancient river valleys and lake beds that speak of an earlier climate. Titan provides active analog processes, though with different fluids and materials. The combination is scientifically powerful because it broadens the set of known planetary climates and surface chemistries beyond the water-centered case. Titan's thick atmosphere adds further weight. A dense nitrogen envelope supports a rich ionosphere, a global haze, and complex chemistry that is accessible to remote sensing and in situ measurement. It also moderates surface conditions and creates a stable environment for long-range flight exploration by rotorcraft. The planned Dragonfly mission reflects this, aiming to traverse Titan's surface and measure organic chemistry and geology directly. Titan's atmosphere, therefore, does not only create scientific questions, it also enables certain kinds of investigation that are difficult on airless bodies or on worlds with very thin air. Mars has an atmosphere, but it is far thinner and offers different constraints. Titan's atmosphere changes the engineering landscape and the observational possibilities. At the same time, Titan's value does not diminish Mars. The two worlds answer different questions. Titan is not a substitute for Mars as a target for understanding early Earth-like conditions. Mars is not a substitute for Titan as a target for understanding organic haze chemistry and hydrocarbon climate cycles. The claim that Titan might surpass Mars in importance can be grounded scientifically by defining importance as the breadth of coupled processes available for study in one place. Titan couples upper atmospheric chemistry, aerosol formation, thick lower atmospheric dynamics, active surface liquids, sediment transport by wind and rivers, and a likely subsurface ocean, all within a single coherent system. The Moon therefore serves as a testbed for planetary science that spans atmosphere, surface, and interior in a way that few other bodies offer. In the deepest interior, Titan is held together by rock and high-pressure layers, warmed slowly by long-lived heat sources, and structured so that a liquid ocean can persist beneath a thick ice shell. Above that interior, a surface climate operates with methane as its working fluid and with organic chemistry as its continual output. The world presents an unusual unity across scales, from deep heat to surface seas to high haze. Observations indicate a layered structure and an active present climate. It remains uncertain how methane is maintained over the longest times, how the ocean interacts with a rock, and how often the surface and ocean exchange material. Even with these uncertainties, Titan stands as a singular scientific destination, not because it resembles Earth, but because it expands what a planetary system can do. It shows that a cold moon can host an atmosphere like a planet, seas like a world, and a hidden ocean like an icebound interior, all at once.